It's my pleasure to be here, rather short notice. And what I want to do today is talk about rare earths. You see, it's a very broad title I was suggested here. It's a very nice title. It's so broad that it hardly fits on the slide. So I need to be rather quick, but I want to basically draw a very general picture of rare earth supply and demand, and with this define criticality. I want to talk about criticality. That's a theme through my talk, and want to then go along reduction, recycling and substitution, and before that really place the magnets into the scenario of materials for green technologies. So I give this as an example. I want to explain to you briefly how a permanent magnet works and why we do need these rare earth elements, and why do they make these magnets so special. So I'm from the Technical University of Darmstadt, but also I'm one of the scientific directors of a newly founded Fraunhofer project group. It's IWKS, which stands for Materials Recycling and Resource Strategy. So this is founded 2 years ago with the aim to be fully independent in 3 years' time. So we are investing a lot of money into these strategic issues of criticality, substitution and recycling. Okay, I start very broadly, talking about renewable energy, wind, water, sun. So we have, of course, on the left-hand side, we have the cyclic dependencies. You're all very familiar with this. Day, night, seasonal and geographical distribution. On the right-hand side, we have our needs for residents, for mobility and industry. And left and right-hand side, of course, do not match. And there we need new materials and new technologies to actually facilitate that match. And basically what I want to show here is that magnet materials, although often overlooked, are actually key components at all these stages of conversion, storage, transport, and reconversion. Permanent magnets in wind turbines, in electromotors, soft magnets, also in energy, electricity conversion, transport. And here, just very briefly sketched, magnetic refrigeration. That's just something I want to mention briefly. That is a new solid-state-based cooling technology which could eventually replace, at least at some markets, conventional compressor-based cooling. That's a very energy-efficient cooling technologies, and for that we also need a lot of permanent magnets. So all this is very nice, but then let's say there's this efficiency paradox that we historically never achieved any decrease in energy consumption. No matter how much better we made materials or technology, we always had rebound effect, and the opposite is true, that we always had an increased energy consumption, and if more efficiently, but still increased. So that is, let's say, the backside of the story we should keep in mind. So in Germany we talk a lot about the Energiewende, the energy transition, or let's say the exit from nuclear and fossil fuels. So it's a bit difficult to translate, I find. So what I want to say is the Energiewende is eine Materialwende. That means it's also a change in materials. We need to look into the material issues, what we need for this energy transition. And what is important, it definitely aggravates our dependencies on strategic metals. That is one key point here. So if you look at this for criticality matrix, that is one of many possible presentations here of Department of Energy, and it plots the supply risk for certain elements against the importance to clean technology, in this case for photovoltaics, electromobility and wind turbines. And you can see that the light rare earths, neodymium, and especially the heavy rare earths, dysprosium and terbium, but also europium, are ranked also in a midterm perspective as highly critical. And at Fraunhofer, it's our new group, we define criticality in a very broad way. That means we not only look at the simple geological availability, we also, although difficult to quantify, we look into the geopolitical factors, economical developments. We look into the ecological consequences and also the technical developments. That also means the coupling of elements while we extract them. Yeah, so all these strategic elements are usually secondary, tertiary, let's say, products of primary, very common metals to be extracted. But also we have competing technologies. For example, I mentioned magnetic refrigeration. If that takes off, we would have immediately a very big new demand for rare earth-based permanent magnets, and with this an increased demand for the rare earth elements. So criticality is very much dynamic. Here you can see that these specific, we call them also like the spice elements. That means just a little pinch of it changes the functionality of a component drastically. So that is meant with these strategic metals. And you can see that 80% of the extraction of the rare earths, the platinum group metals, gallium, indium, and so on, took place in the last 30 years. There's a very new report by the European Commission. It was published last month on critical materials. That is an update of an earlier report. And it's interesting, just a couple of examples here. World primary supply of 54 candidate raw materials, and then more specifically of 20 critical metals here. And you can see how these are globally distributed in terms of the supply situation. And of course you can see that the European EU, for example, only occupies a very tiny box there. So that is of course a big issue here, that we find efficient strategies to have a sustainable supply for the development of these high-tech technologies. Then this is the static range. I should emphasize the static range of certain elements. And you can see these are very, let's say, close time scales. Yeah. So if you want to show some of these to your children, you better buy them now. You can see that some elements have a very, very low range. Of course, there's the argument that we always find new reserves. That is certainly true. But we will need always more and more energy and more effort to actually get hold of these, let's say, ores, which are likely to be less and less concentrated. Then I talked about the coupling. So this is about the metrics of metal ecology. Here I just want to show that we have in the inner circle the primary common metals to be mined, and then on a secondary and tertiary level we have these more strategic elements to come. So for example, there's the aim to make lead-free components, lead-free batteries. So if we stop for that reason, if we succeed in making lead-free batteries, then we might stop to some extent the lead mining. And you can see there's a whole sequence on these secondary and further levels where these strategic metals are, of course, affected. So that's what I mean with a coupling of metals in the extraction. So the rare earth oxide supply, we had an era where the US with the Mountain Pass mine was dominating this situation. But more recently, and all of you will have heard about it, it has been in the newspaper many times. China is of course dominating the market, and now we can. It's about something like 95% of all rare earth oxides are exclusively monopolistically produced in China. We had 2 years ago, almost 3 years ago, we had the so-called rare earth crisis. Due to certain events, political events and so on, there was a huge price change triggered. We had 3,000% of price changes for certain rare earth metals. For example, here plotted for dysprosium. Now things have calmed down, but we are still on a significantly higher level than before this so-called rare earth crisis. So here, and we still have. On the right-hand side, you can see that we have about 20% price changes easily within a couple of months. So that's still a very volatile situation. So what we want to have are these nice, clean, pure rare earth metals or metal oxides. The situation of the mining is actually the opposite of clean. Yeah, we talk about green technologies, but the metals are certainly at this stage not green. So we have a big issue there that the mining is done under very environmentally problematic conditions, and it needs to be seen how the new mines which are on the way in California or in Western Australia actually can prove that they have a sustainable, let's say, closed cycle setup there. Then, of course, I don't think we should, let's say, really blame China for that situation. I think, first of all, the West has to blame itself, because it was very clear that China has, and they never made a secret out of it, that that is a strategic material. And one reason we are in this monopolistic supply situation, that the West, of course, was quite happy to get rid of these environmental problems related to the extraction and basically export this as well. So this is the situation. And if you look at this right-hand picture, for example, in Malaysia, that is one of the new mines, no, not mines, but the separation facilities where liners from Australia, again, to some extent, export that situation and have the refining done in Malaysia. So again, there's a lot of legislation and issues related because, first of all, we have radioactive, let's say, elements, thorium, uranium involved in the mining, so they end up in the tailing and you have to keep them somewhere. You make sure that they don't dissipate in the dust or in some water. So at Fraunhofer we try to understand, and I will be quick here, what is called, we call it the geography of a metal in time and space. So we really try to understand what happens from the ores to the refining to the production of certain alloys to make it into a magnet, for example, and put it into a motor, and then it becomes especially interesting and especially difficult on the right-hand side. You see these so-called rephases, reuse, remanufacture, recycle. That, of course, and I come to that in a second, at the moment, at this time, there's no recycling of rare earths happening. So that is, of course, a big issue and a big challenge, actually. So here you can see this nice plot by Gradle. You can see the recycling rates of certain metals, and you can see that cobalt, nickel, copper, and so on, they have significantly high recycling rates, far beyond 50%. But all the lanthanides, this is a group of the rare earth elements, which is, let's say, the focus in this presentation. The recycling rates are below 1%. So that is, as I said, I think that is a big, also, opportunity. Then it is interesting to see that the complexity of materials and components has evolved a lot. So basically in your smartphone, of course, you have more than 40 different precious, more interesting metals. And that also means that the recycling becomes more and more difficult because we have all these different metals at very specific places, maybe in low concentrations. And that's, of course, we want to save these materials, so we find new technologies to put them into thin films at a certain place where they should function. But that complexity, of course, makes it more difficult to recycle and to avoid that these materials simply dissipate. A metal, in principle, can be used forever and ever again. But it can be, of course, the rare earths at the moment, they end up in some iron, steel waste and are diluted and in a way dissipate and disappear. So what we really need also, and that is one of the topics at the new Fraunhofer place, is that we look into advanced design for recycling. So that we try from the very beginning to design a component differently so that we can extract it later more easily. So I said 95% of the rare earths come from China, 80% of the permanent magnets produced worldwide. This is a sintered neodymium iron boron high-performance magnet. That is a magnet with the highest energy density. They are coming from China, 18% of Japan, and the biggest Asian producer is, well, not so far here. And we need about 600 kilograms of sintered neodymium iron boron per megawatt produced in a wind turbine. That is for a direct drive gearless wind turbine. That sounds a lot, but at the same time it means that with the energy density, the volume and the weight will be reduced significantly, and that we also in turn have a much reduced demand for copper, for steel, for carbon fiber, and so on, and of course much improved maintenance. And then for a hybrid vehicle we need about maybe 2 kilograms of neodymium iron boron for motor and generator. And it's important to say here, these technologies do not eat up much of these 100 or 120,000 tons produced at this stage. Yeah, these are markets and technologies which are to come. So they are not yet really using the material produced, and that of course puts the perspective of the rare earth supply and maybe the criticality again. So that is a slide I borrowed here from CWIEME, and just explains, of course, the high energy density of a neodymium iron boron magnet. But at the same time, it's actually interesting, just what I ask my students, what is the chemical energy involved in this energy density of a permanent magnet? So 1 cubic meter of neodymium iron boron weighs 8 tons, but the energy density of that is only half a schnitzel. Yeah? So that is difficult to imagine if you see how powerful they are. But these magnetic energies are very, very small as compared to chemical energies. But of course they are the material of choice for all these applications. And here on the right hand side you can see very briefly how these traction motors, let's say, scale in terms of material input and cost. And of course neodymium iron boron plays a significant role here. So how can we tackle now the rare earth supply risk? We have the option, of course, we need sustainable primary mining, and I wouldn't consider that that's sustainable, but of course there's this deep sea mining, possibly at some stage in the future, where you hoover the ground in 4,000 meter depth. Yeah, most likely not very sustainable. And that is of course something we pursue. We want to use more efficiently the critical elements. We want to put them where we really need them in the microstructure, and don't dilute them in the volume, which is done conventionally, and also buy in a lot of negative effects. So that is what is the idea of what is called grain boundary engineering. So we put these heavy rare earth elements only at these internal interfaces in a magnet, and I give an example very briefly. But also then efficient shaping is an issue. Yeah, at the moment we make complex shapes by simple machining of a ring segment, and we waste again 20–30% of these materials. And then of course recycling, and I put here, you will never walk alone. Some of you maybe know that. The problem with rare earths is they always come together. Yeah, they never come separately, they always come together as a bunch. And if you want to get hold of neodymium, of dysprosium or terbium, we end up basically producing loads and loads of piles of cerium, of samarium and lanthanum, for example. And that's also something I come back in a second to, is the so-called rare earth balance. How can we address that? And how can we make use of all the other, let's say, rare earth elements which we produce in any case? So that's the value chain, very briefly, of the rare earth ores, the mixed concentrate, the separation, and so on. And then that is mined to market. And the question is, can we make use of urban mines? That is not done at the moment. There are no logistics in place. Yeah, the disused motors are just going somewhere. And that is a big issue to actually make an efficient logistic collection network to get hold of these magnets again. So then we would basically, and then we could think where we would go back into the chain. Of course, we don't want to go back far. We want to either reuse the magnet or maybe go back to the intermetallic component, and want to avoid that we need to separate down to the individual rare earths again. And again, this is a graph from this report where you can see the supply chain for permanent magnets, and the orange color, which is that what is happening in Europe here. So of course we basically start then with alloys here in Europe. Again, I just refer you to this report. I don't have the time to explain all these figures, but it's very informative. It shows you, for example, that the reserve situation is actually a bit more positive. I told you that a lot of the, more than 90% of the oxides are produced in China, but actually it's about 50%, which actually in terms of total reserves is estimated to be in China at this stage. Yeah, so there are significant other reserves in other countries. And again, you can see here, I'm not going through that, to which extent, which element, rare earth element is produced in which country. I will be quick here. What is new in this report, and it's something, of course, we proposed for a long time, we have to distinguish between the light rare earths and the heavy rare earths. That is very important, yeah, for magnets. And here you can see the supply and demand forecast. And you can see here that the magnets will be increasing. That doesn't look very big. It still means it actually doubles. So that is a huge increase to come for the magnets. But you can see also that in principle, the supply situation is not so problematic. We do have enough rare earths in the Earth's crust. And the question is, are the new mines going to be economically viable? That is a big challenge. And then actually, you can distinguish that for light rare earths, and here it's clearly seen that light rare earths is in principle not a problem, but the heavy rare earths, and we need the heavy rare earths for the thermal stability in a permanent magnet. This is actually a very problematic situation, but this is where we as material scientists think we can solve that situation. Okay, and then again, I refer you to this. You can see this supply and demand forecast and where these materials are used. So neodymium, of course, is going to be used in magnets a lot, and we will see that it's a relatively tight scenario. It is not clear how that develops, if we will have a certain surplus maybe, or if we have a certain deficit. For terbium, it is more clear. We will certainly run into a deficit situation. Also dysprosium. But then the others, cerium, lanthanum, praseodymium, samarium, there we will have a significant surplus. And this is summarized here again. Yeah, the surplus for the cerium, reasonably tight situation, also in a midterm perspective for neodymium, and then terbium, dysprosium to be heavy rare earths. These are the really highly problematic elements. So how do we actually make a good magnet? A good magnet, we have an intermetallic compound. It has very good intrinsic magnetic properties. This is the saturation magnetization, the anisotropy field, and the Curie temperature. These are our theoretical upper limits to what we can in principle achieve. This needs to be thermodynamically stable. That means it doesn't decompose immediately or at elevated temperatures. And then we start engineering the microstructure so that we have extrinsic properties, remanence, coercivity, and energy density we can use. And this is then plotted here in the hysteresis graph. And you can see on the right-hand side how this has developed. And let's say in a way, sadly, we are stuck since 30 years with neodymium iron boron. Since the discovery of neodymium iron boron, we have not found a better material, but also this had certain physical reasons, because this structure is actually very close to a perfectly, if we could draw up a magnet, then neodymium iron boron is actually very close to that in terms of its unit cell structure. So what is happening here this energy density is plotted. This is this square here in the hysteresis loop, B over H. And you can see how the energy density or the remanent polarization develops versus coercivity and operating temperatures. So for MRI imaging, we have no temperature demand. We don't need heavy rare earths. But for the motors, we need to replace the light rare earths, neodymium, with the heavy rare earths, dysprosium. Yeah, and we have then the situation, just one very, let's say, short excursion. The iron couples parallel to neodymium, and we remain a high magnetization. Dysprosium, the heavy rare earth, couples anti-parallel, and that's why we have a decreased magnetization, and that's why we have this negative slope here. That is shown up here. But we also have the positive effect that the anisotropy of the dysprosium is much, much higher, so that we actually gain in temperature stability for the application. Okay, so there's a good magnet. You can see the unit cell here. the magnetization loop along easy and hard directions. And to be very quick, just to show how we work as a, let's say, material physicist. This is the microstructure. This is how it looks like, what you have in your motor. And you can see it consists of different phases. This is what is called the backscattered contrast in a scanning electron microscope. So we can see the different phases. And important here is that these little elemental magnets of hard magnetic phase are separated by a rare earth rich phase, one from each other. So they are magnetically decoupled. But that is also the weak link. And somewhere in a reverse magnetic field, the nucleation of reverse magnetization basically nucleates and propagates from there. And that is what we need to avoid and need to understand why is this happening. And if we understand this, then we can use much less of these precious metals. And so we do, to be quick here, a lot of detailed multi-scale characterization. I just show you one example here. This is a high-resolution transmission electron microscopy. So you see the scale here. Yeah, that is only 1 nanometer. So actually we look here at individual atoms, or to be precise, at columns of individual atoms. So that is the resolution actually we then finally work on and try to understand. And you can see here, hopefully, there are these little rings. And these are these rings out of the unit cell. And that's why I say this structure is so close to perfection, because we use little of light rare earth. We use a lot of iron, cheap, abundant, high magnetization, and then another rare earth layer. So that is actually, and then we have this coupling of high anisotropy with high magnetization, even on a unit cell basis. So that is the beauty of this compound. And this again then is, this multi-scale characterization is coupled to multi-scale modeling. So on a computer we can replace one phase with the other and can understand what we in principle should do to make these magnets better. Another way actually is to make net-shaped magnets by hot deformation. So we do this in Darmstadt and Fraunhofer. We have rapidly quenched materials. We can make them into a hot press magnet, and then we can extrude these ring magnets. And then we have quite complex shape with very little waste produced. And you can see on the right-hand side also with very high magnetic properties comparable to the sintered conventional powder metallurgy. The problem here is this is at this stage a discontinuous process. Yeah, so we make step by step, and that is of course makes it economically problematic. Okay, then I want to touch briefly on recycling. Another interesting process is hydrogen processing of neodymium iron boron, the material of choice. And you can see here that you can actually decrease, this is a seed motor, yeah, by replacing a conventional ferrite magnet with a first and second generation of hydrogen processed neodymium iron boron magnets. These are polymer bonded magnets in the end. And this is also a way we propose and develop for the recycling, the hydrogen processing. And I will be quick here, not go into the detail. But what we basically do, we use a scrap sintered magnet from a disused motor, and we take the magnet containing component out, put hydrogen over it. The magnet powder will basically fall out because it's so reactive. The earth, they love hydrogen, they jump on it. Yeah? And then we have a very clean single crystal powder here, and this we can make then into a reasonably good polymer bonded magnet. And you can see here in this video, hopefully, this is a piece of neodymium iron boron sitting at room temperature, and 1 bar of hydrogen is flowing over it. And you will see this is only accelerated by a factor of 4, the video. And you can see how violently it reacts. It's a solid piece of metal, and it just falls to pieces in a very fine powder. And that is a process used for the production of magnets, but we want to use it also for the recycling of magnets. Okay, and here's some properties which are, let's say, promising, but not yet on the level of the starting material. So there's some work to be done. Okay, I need to get to the end. We have two major targets in terms of our, let's say, fundamental and applied research. We want to make the existing needle-iron boron magnets better by using less or no heavy rare earths. That is the target one. And the second target is to have completely rare earth-free magnets. And there we need to be realistic. We want to be better than the conventional ferrite magnets, but I don't think we can compete in the near future with the rare earth-based magnets. That is, I would say, would not be a very serious statement. Yeah, and we drew up some lines how we can get towards high-performance magnets in the recent publication here. And the idea is just to give you one or two examples. Iron cobalt has the highest magnetization, 2.35 Tesla, but it's cubic. It has no anisotropy. And if we find elements we could add to this material to make it tetragonally distorted, to have some anisotropy, then we would have an interesting material for a permanent magnet. So that would be one strategy, what I mean with non-cubicity. Okay, and here there are a number, if somebody has questions there, these are all interesting compounds one can look at in terms of rare earth-free, let's say, new, I put sort of in a hyphen here, because a lot of them are actually quite old and a little bit forgotten, and we dig them out again and look at them again now. That is very interesting. It sounds exotic, but it's very interesting. L10 is a specific structure with a very high anisotropy. Iron platinum is used in magnetic recording. We need very little amount of it, so we can afford it. But of course, to make a bulk magnet is not possible to pay. But for example, iron nickel is a cheap material. And what you find, actually you find them in meteorites. Yeah? So they had billions of years to get into the right structure. The phase transformation we need is at very low temperature. So we have every 10,000 years, we have one jump of atom going to the right direction. So it's too long for a PhD or something. But now we try to find, of course, extreme conditions. How can we get into this ordered structure, which would have very interesting magnetic properties on an earthly timescale, by severe condition? Okay, I need to finish. Another example for a new lanthanide-free hard magnetic material we have developed in Darmstadt has a high magnetization, high Curie temperature. So the question is a hype over for rare earths or is it not? In my opinion, nothing has changed in our, let's say, boundary condition. The supply and so on, the situation, the production, nothing has changed. So it could happen any day again that we get into what might be called a rare earth crisis. So I will be brief on that. One example, magnetic refrigeration, to finish here. Yeah, we will have a very much increased demand in air conditioning in the so-called BRIC countries to come. So that is a huge challenge we have to face. So if we can have an alternative magnetic-based cooling scenario, which is a couple of % better than the conventional one, it might be very interesting to look into that. And so I conclude by saying, at the moment, we have no equivalent substitutes for needle-iron boron magnets in many applications. There are options or possibilities that we find rare earth-free permanent magnets potentially technologically disruptive. They need to be better and, let's say, almost equally cheap than as compared to the hard ferrites. The supply situation is a complex one. I try to allude on a couple of points. Light and heavy rare earths are, of course, completely different. But important is that the big demands in electromobility and wind turbines are in principle still to come. And finally, we need to look into recycling. That's technological, scientifically a big challenge, but I believe that is also a big opportunity commercially. In Darmstadt and in Fraunhofer, so if you are interested in these topics, please write to me, talk to me. We have different programs where we really look into all these issues. We are setting up pilot lines for magnet production and recycling. And finally, there are some, if you want to read some of the, let's say, material physics and general issues, we have published this. I want to thank many institutions we work with. This is our group in Darmstadt. So I thank you very much for your attention.